welcome everyone to week 3 of the PCC CHanGE seminar. To remind you, we're this year for the PCC seminar, we're collaborating with the Center for Health in the Global Environment to talk about, have conversations about climate change and health. So, and we're pairing 2 speakers who are going to talk for 20 to 30 minutes. Then we're going to have questions from the general audience. And then I'm going to excuse the general audience, and then we're going to have the students do breakout rooms, come up with more questions, and then have a conversation with the speakers. So before we get started, I wanted to do a land acknowledgement. And this land acknowledgement was put together by the graduate students in the program on climate change, communicating climate change last quarter. Land acknowledgement. As we begin our gathering, we respectfully acknowledge that our event today is taking place on occupied Coast Salish land and that the University of Washington is on the homelands of the Duwamish people. We pay respect to Coast Salish elders past and present and extend that respect to their descendants and to all Indigenous people. To acknowledge this land is to recognize its longer history and our place in that history. It is to recognize these lands and waters and their significance for the peoples who lived and continue to live in this region, whose practices and spiritualities were and are tied to the land and the water, and whose lives continue to enrich and develop in relationship to the land, waters, and other inhabitants. So this week, we're going to be talking about attribution, and we're going to look at it from 2 different perspectives. And Kristie Ebi, who's a professor in global health, and I'm sure professors in other departments in health as well. She came to UW within the last decade and founded the Center for Health in the Global Environment. And she's going to kick us off. And then we're going to get Dale Durran, who's from the Department of Atmospheric Sciences, who's going to be talking about aspects of communicating and defining attribution for climate extremes. So I guess I'm going to let I think you can share your screen, Chris, so we'll go ahead and get, yep.
There we go.
Okay. Yep, looks good.
All right, and we'll see if I even get to 20 minutes. I've got a pretty short presentation. I don't know if Jeremy covered this last week, but it's an overview figure of a paper that we worked on and published in December to try and give a sense of the complexity of when we talk about the health risks of a changing climate. That at the very top, you can see we've got global environmental changes, we've got climate variability and change. We could combine those, but we did want to pull out climate variability and change because of the exposure pathways that are important for health. There's also socioeconomic drivers. And all of these interact with vulnerability and susceptibility. So interact with a variety of socioeconomic factors, diversity, lack of access, a whole range of reasons that some populations are poor and marginalized, and reasons that populations live in places that are highly vulnerable to our changing climate. So you can see there's a complex interaction here that then leads to a very wide range of health impacts and future projected risks. And I've got major categories at the bottom. Within each one of these are a long list of climate sensitive health outcomes. It's important to start out with this because when we talk about detection and attribution, it's more complicated to think about how you detect a change in a very complex system and then determine the extent to which climate change may be driving that change. What I didn't put on here explicitly is that our health systems, which are all of the activities that try to protect and promote our population health, continually evolve. That health systems change over time. And so trying to understand when you see, for example, a change in the prevalence of an infectious disease, how much that has to do with the disease transmission and the drivers of disease transmission, and how much has to do with various control programs. which is a long way of saying the health sector is only recently coming into the detection and attribution space, just because of the complexities of the system. When we think about detection and attribution, they are formal methods that are used to determine whether a system has changed from a baseline and the extent to which climate change has contributed substantially to that observed change. As I implied in the slide before, one of the challenges in health is we don't have specified baselines. We do have several years of data, several decades of data in some places for climate sensitive health outcomes, but we don't have the kinds of records that you have in climate science. And we haven't ever gone about the process of establishing a baseline from which we determine whether or not there's been a shift. So that in and of itself is quite a big challenge. And then looking at the attribution piece is actually fairly interesting. There was an IPCC expert meeting on detection and attribution in the 5th assessment cycle. Myself and another epidemiologist were there. And when you look at the methods used today for attribution, they're really informed by what we do in health and think about attribution in health. It was a great multidisciplinary set of discussions about detection and attribution. And then you can see in the bullet point that attribution is complicated for health because there's so many things that influence the burden of a particular disease. Control programs, weather, environmental variables, socioeconomic change, land use change, trade, tourism, and I could keep going on. And so trying to find situations where it's possible to do detection attribution is complicated. So with that as a background, I'm sure we're going to hear from Dale that much of the work that's been done in the climate science has been based on modelings where you can do detection and attribution within one model. But for all of the impact sectors, health, ecosystems, and others, it's at least a two-step process where you first establish a baseline that you're going to use as your reference period. Look at how you can structure it so that you can isolate the system of interest from all the other drivers that are going on, so that you can determine whether or not there has been a change from whatever your reference period is. And then the attribution, as I said, in the climate science is often a single comprehensive model. But what typically happens in the impact sector is it's a two-step attribution after you've done the detection. And you want to look at whether there's been an observed change in a variable of interest, a variable that's associated with one of the climate sensitive health outcomes, and then look at the extent to which the change in that variable has been affected by anthropogenic climate change. When you look at event attribution, which we're going to hear quite a lot about, it is a basis for most of the work that's been done, not all of it, but most of the work that's been done in health on detection and attribution. And I've got a URL there for World Weather Attribution run by Freddie Otto and some of her colleagues in the UK. And they do rapid event attribution where an extreme event happens and they do, within a couple of months have an attribution of the extent to which climate change might have affected that. And I have two examples here. One is work that was done on the Australian bushfires. And you can see the drivers: drought, heat, climate variability. And although the heat extremes increased by at least a factor of 2 because of climate change, so they could say that at least some of this was due to the heat extremes, there really wasn't an attributable trend in terms of drought. Although when one read about the event, there's lots of emphasis on the drought, not just on the heat. Also have here a tropical storm, Imelda, which was a 1 in a 1,200-year event, where the detection and attribution said that climate change made the extreme rainfall and flooding more likely and intense. I didn't put on the slide, but I should have mentioned every year there's a special issue of the Bulletin of the American Meteorological Society, BAMS, where there are usually up to about 20 or so detection and attribution on extreme events. And they're quite interesting to look at to see from using these formal statistical methods of which events you can say had something to do with climate change and which you really can't. And then when we do have detection and attribution of an event in health, we can use this. So this is one of several examples on heat. It was July 2018 in Japan. You can see the temperatures on the upper left, very high temperatures. In fact, the heat wave was declared a national emergency where tens of thousands of people were hospitalized and more than 1,000 deaths. One of the interesting pieces about this particular heat wave is there's different ways to think about your baseline and different ways to go about this formal statistical process, depending on how you define the event, what exactly you're looking at. But basically, this event had about a 20% probability of occurring in today's world, with a 0 probability in a world without anthropogenic climate change. So that's all well and good. One of the challenges for the health sector is, for this event or any of the heat events, is if the event had a 20% probability of occurring today, what proportion of those deaths and hospitalizations do you say is due to climate change? Do you say it's very unlikely this event would have happened and you basically attribute most of those hospitalizations and deaths? Do you take the 20%? Do you plot out the probability density function and look how it shifted, match that with the health data and just take the extremes as what you would consider to be due to climate change? This is an area of active discussion, and it's something that hopefully there'll be guidance later this year on how to think about when you have these extreme events, when there is not 100% attribution to climate change, how you think about how much of the impacts could be attributable to climate change. That is relatively straightforward. It becomes much more challenging when you start looking at other climate sensitive health outcomes. So I've got an example of Lyme disease. Lyme disease is a complicated transmission cycle. There's a 2-year transmission cycle. The disease is transmitted by a tick, and the tick lives around, is associated with a kind of deer. Lyme disease used to not exist in Canada. It does now. And when you look at this complicated disease transmission cycle, that climate could impact the disease transmission either by affecting the tick vector and distribution, by affecting the pathogen's transmission cycle and its efficiency, or by affecting the likelihood of transmission to humans. So you have to think about these different pieces of the transmission cycle, how climate plays into those, and then how to go about thinking about the detection and attribution. And I'll show you some work from Nick Ogden, who's been working on this issue for many years in Canada. And so you can see the top figure is 1971 to 2000. And you can see the darker the color, the higher the probability of disease emergence. And in fact, there has been quite a bit of work. Sorry, this is United States, it goes up into Canada. There's been quite a bit of work projecting what could happen with Lyme disease in a changing climate. And as a result, the Public Health Agency of Canada has been doing some active surveillance for the ticks. And so it's actually monitoring the tick as it changes its geographic range. And as a consequence, then there's other activities that have taken place that, for example, physicians, healthcare providers, until recently didn't learn about Lyme disease in particular in some of their courses because it was a disease that didn't exist in Canada, but they do get cases now. So there's been a work to educate healthcare providers. Anyway, you can see over time, the projections just showing an increase in the geographic range well across parts of Canada. And so this is an area where they're doing quite a bit of work. Worked with Nick on a paper, came out in 2017, and based on what's known about the transmission cycle and about what has happened with climate change in Canada, concluded that the increase in the geographic range of Lyme disease in Canada could be attributable to climate change. And I wanted to mention a third category as well, that there is a tendency when you do detection and attribution to look at the big impacts, the places where you're going to get big numbers. This is a paper, part of a paper published in December on detection and attribution. And one of our case studies were ice roads in the Western Arctic. And so you can see there was a detection and attribution study for the winter of 2017 to 2018, when there was the extremely low sea ice cover in the Bering Sea. It was considered a 2 in 1,800 year event. In December of 2017, a flyover said that there were so many open water holes that they could not be counted. Ice roads, of course, are critically important for northern communities. That's how they get from one place to another. And we don't do a very good job. Collectively, we don't do a very good job looking at what the health consequences are. So there's very few data on what the health consequences are. We've got some indications of people who disappeared because open water, they didn't know that the ice was so thin, there was open water, and didn't come back. We've got a little documentation, for example, of some accidents related to the amount of open water. It was interesting in putting this paper together, the reviewers were extremely strong that they wanted this removed. They said the numbers are too small. And we argued back to the journal that the numbers might be small and we might not have very good data, but this is a critically important issue for northern communities. And the fact that climate change is affecting them through the impact on the ice roads is an area where there should be more research and we should have greater understanding of what this means. The detection and attribution is not just for the big numbers of the 70,000 excess deaths in heat waves in Europe in 2003, but really should be brought down to a more community level so that people can see what climate change means to their own lives and the kinds of changes that have already happened to them. In terms of the next steps, have discussions with several groups who are looking for events where you've had detection attribution on the event and trying to see where we can get the health data to get some estimates of what the health consequences of these events are. It's not always easy. As I said at the beginning, you have to have a baseline to figure out when there's been a change. And you need a long enough data series to determine trends. And there's a few places we can do this. There's many places we can't, even though it's likely that that if you could do a DNA, that there would be significant impacts on health. We're going to hear a lot more from Dale about how you go about doing event attribution, but this is an excellent opportunity for partnerships between people like Dale and people in the health community to start providing quantitative information on how climate change has already affected human health and well-being. This is very important for policy. Instead of doing this for 25 years, instead of going out and saying, yeah, there's associations between weather and these health outcomes, weather changes, we'll see impacts on health. It's another thing to be able to go in and say, we can count it and we can tell you what the numbers are. The numbers are small at the moment, but then we have not done much work in detection and attribution. And of course, as the climate continues to change, those numbers are only going to increase. And that's everything I was going to say, Luann.
Okay, thank you. Okay, we'll move on to Dale. So Dale, do you want to share your screen?
Sure. Okay, you should have that up, I think. And let's also grab one thing real quick here. Oh, I don't have it. Okay, never mind. So what I'd like to do actually today is not try to give you a super quick overview of everything related to climate change attribution, but to actually present some what I hope are new thoughts about this related to an article that came out this fall in the Bulletin of the American Meteorological Society. As Kristie noted, one major foundation for climate change attribution has its roots in epidemiology. And I'd like us to think about where we might be if we also extend our roots back to weather forecasting. Okay, so a risk in the attribution of an extreme event include underestimating the role of climate change, which obviously fails to properly alert the public. We can also overestimate the role of climate change, which helps create climate anxiety and potentially derails public discussion with false alarms. And how do we balance these two things? How do we balance, say, failure to warn and crying wolf? Okay, so the idea is weather forecasters have long confronted the balance between over and under warning. And what we have here is an example of something called a mesocyclone that may or may not have a tornado drop out of it. This is part of a severe thunderstorm. And so let's just take a moment to review a little bit of basics for weather forecasters. So let's suppose we have some weather forecasters who want to know who's the best, and they're trying to forecast tornadoes during a period in which there were 80 tornadoes. Okay, we got first forecaster is Jane, who's issued 200 warnings, 60 of which are correct. Then we got Jennifer, who issued only 10 warnings, but all 10 were correct. And finally, Jacqueline's kind of in the middle with 100 warnings, 40 of which are correct. Okay, so if we ask who's the best forecaster, well, we need some measures to assess who's best. And of course, the Weather Service has been worried about this for a long time. So let's look at this from the standpoint of how the Weather Service would assess these. So scoring the forecast, we look at the possible outcomes, and we're going to look at situations where you have a yes-no binary outcome, which is often what the public really wants in terms of attribution, whether it's what climate scientists really want to give or not. So possible outcomes are a warning is issued and the event occurs, so we'll call the number of these A, and that's a hit. That's good. We have a warning is issued, but the event does not occur, B, that's a false alarm. Or no warning is issued, but the event does occur, that's a miss, C. And then there's one fourth possibility, no warning is issued and the event does not occur, but this situation is not highly relevant for extremes. For example, there are many, many days when there's obviously not going to be a tornado in Oklahoma, and you don't get credit for having made that forecast in the middle of January in Oklahoma, for example. Okay, so for scoring now, we have a couple measures, the probability of detection, which will abbreviate POD, which is the ratio of correctly warned events, so that's A, over all events that actually occurred, so that's A plus C, all the actual events. And the other one that's important is the false alarm ratio, which we'll abbreviate as FAR. And we'll come back to this FAR business in a moment, because it's also known as a fraction of attributable risk in climate attribution studies, but it's different. So right now we're in weather world, and the false alarm ratio is going to be the falsely warned events over all warnings. So that's going to be B over A plus B over all warnings. Okay. So now if we score our forecasters here, the story is Jane with 52 hits out of 200 warnings has a probability of detection of 0.65, 65%. One is perfect here. She's the highest because she got the most tornado warnings out when tornadoes occurred. But she also has the worst false alarm ratio, 0.74. Meanwhile, Jennifer has a perfect false alarm ratio, never put out a warning when a tornado didn't happen. On the other hand, has a very terrible probability of detection at just 0.125. And then Jacqueline got half the tornadoes right, so has a probability of detection of 0.5, and her false alarm ratio is better than Jane's, 0.69, right? So we look at this, there's two reasons we're going to use these numbers. The first one, which we can see right on this graph, is I want you to note that in formulating strategies, if we try to reduce the false alarms, which of course we don't want, that's what Jacqueline did relative to Jane, we reduce the probability of detection as well, and we reduce it by more. the change in the probability of detection is 3 times the change in the false alarm ratio. And what happens here relates to the quality of our detection system. Given a certain system for detecting things, we can't just do whatever we want. If we want to lower the probability of detection, it's going to cost us, we don't want to lower the probability of detection. If we want to lower the false alarm ratio, it inevitably leads to a change in the probability of detection. And in many cases, it leads to a bigger change in the probability of detection. We'll talk more about that. But notice that was the case for this little hypothetical example. Okay, let's move out of the hypothetical world and ask, hey, what actually is the story with tornadoes anyway? What is the current false alarm ratio for tornadoes from the National Weather Service? And so here's a set of choices. And if we were in person and had more time, it actually ask you to raise your hands, guessing which one is actually correct. But I think we should keep moving, and we're kind of not in person. So the story is in this following graph. Here's the National Weather Service performance from 1990 through 2017. And the false alarm ratio, excuse me, the false alarm ratio is plotted in red up here for each year, and it's kind of bouncing around, but its average is about 0.75, and most recently it's about 0.70. So that means that 3/4 of all tornado warnings are false alarms. Meanwhile, we also have the other important measure, the probability of detection, which started out fairly low in the 1990s and rose up to a much higher value, around 0.7, 0.65, something like that, for a period of time. And then we suddenly had another behavior about 2011, where we got a little better false alarm ratio, a little lower, but we had the probability of detection drop quite a bit. Okay, so what's going on in these periods of change? Well, the improvement in the early 90s was related to weather radar and better computer models, better forecaster training. Everyone loved all that. But what about this other period where you could say, well, I'm not so sure things have improved here because the probability of detection has dropped off, even though the false alarm ratio has dropped some as well. Okay, so we'll get to that in a moment. But before I do, let me point out one more thing here, that this performance in the mid-2000s was like Jane, and this performance out here more recently since 2011 was like Jacqueline, right? So we had a reduction in the false alarm ratio from Jane to Jacqueline in real world too, and it was also accompanied by a real world reduction in the probability of detection. Okay, so what caused this change in about 2011? Well, the story is that 2011 was a very, very bad year for tornadoes, including the Joplin tornado, which left 158 dead. It's the deadliest single tornado since 1947 and 7th deadliest in US history. And here's some of the aftermath. It took out a hospital in downtown Joplin. You can see the ambulance entrance here. And it looks like it's been a war zone, right? Things are all burnt up as thick cars caught fire and the building was destroyed. Well, very badly damaged, not destroyed, but very badly damaged. There was an investigation. One finding is there is evidence of high false alarm rates during the storm-based tornado warnings officially issued for Joplin might have desensitized people and maybe led to problems. And so that led actually to the Weather Service changing its practices to try to cut down on the false alarm ratio, and which led also to the decrease in the probability of detection. And it's been backed up by some studies we won't get into. But it's interesting, the deliberate change without actually an improvement in the warning system to drop that false alarm ratio, dropped the probability of detection substantially. Okay, so how important were the false alarms? Well, it's actually a little controversial, actually. This is a really bad tornado. Here's one of my favorite damage pictures from this tornado is actually this one. Recognize these things. These are parking bumpers that are fixed in parking lots by rebar. And the tornado picked these things up and threw them, right? It picked up 300-pound parking stops and threw them 60 feet. Well, in a situation like that, you're in trouble if you're on a tornado shelter, right? And I don't want to get into this much, but the path of the tornado was right through the heart of downtown. So it's just a very, very bad tornado. It's not obvious the false alarms are a big problem. In order to keep moving, I'm going to skip over the rest in this slide. Okay, so now let's get to extreme event attribution. So let's move away from severe weather warnings back to this question of, well, climate change is changing our severe weather. There's lots of differences between these two things, but there are some commonalities too. And in particular, they both have the goal of properly alerting the public about atmospheric phenomena that can have dramatic impacts on life and property. And also another interesting thing that is not necessarily as widely recognized in the case of tornadoes is there's a significant fraction of the low-income population that's potentially affected that really can't do anything in response to these warnings. So of course, we know that's true for lots of disadvantaged and poor areas under climate change, but it's also actually true for tornado warnings in many circumstances as well. About 20% of the population in the southeastern US lives in mobile homes. And if you live in a mobile home, the warning is more or less worthless. You don't want to be in your mobile home, but most of these mobile home parks don't have tornado shelters, so you're out of luck. There's not much you can really do that's practical. Okay, so let's get now on to some further discussion of extreme event attribution under climate change. There's two major approaches: the risk-based approach, which is this one that comes from epidemiology. And the idea is you estimate the changes in likelihood of an event arising from climate change. You create two populations where you have statistics to compare changes in frequency or probability of occurrence of a given event in the factual world as it is, that is the warm climate, or the counterfactual world, the world as it would have been without climate change, which is sort of the control climate. And we'll get to that in a moment. In fact, we're going to pay more attention to that. But there's also something called the storyline approach that I don't have time to talk about, but it takes a different approach. It says, it tries to estimate the best estimate of the contribution of climate change to the various physical factors responsible for the event. And the emphasis is on the size of the effect from these factors rather than statistical significance. So I won't say more about that approach, but I want to talk about the risk-based approach and present the relationship there between what we do in meteorology. Okay, so the risk-based approach asks, was a given event caused by global warming? And Kristie alluded to some of this in her previous talk. And the idea is, of course, we'd rather avoid simplistic yes/no answers and compute things that tell us how much more likely this event was in the warmed world. So we have things like the risk ratio. So the notion is we've got a probability distribution in the climate that was not warm. The counterfactual or control world is shown as sort of some sort of Gaussian distribution in this green curve. I hope you can see my cursor. And the factual world, the actual warm world, has a new distribution given by the red curve. And in fact, I'm going to think about stuff related to observations. This can come from climate models, but we're going to focus on actual temperatures in a moment. Just imagine that we have these two distributions, and then we have some threshold for our extreme events shown here. And the idea is the probability that this would occur in the unwarmed world, the controlled climate or counterfactual world, is given by this part of the distribution that's in the green that exceeds the threshold, and that's called P naught here. And then there's another part of the distribution in red that exceeds the threshold in the warmed world. And this ratio P1 to P naught is the risk, so-called risk ratio. And there's also something called the fraction of attributable risk, which is also abbreviated FAR, same as the false alarm ratio, though they're different things. That would be basically how much of this area in the warmer world, P1 is the denominator here, what fraction of that is due to warming? And so we take the difference between the red and green areas and get that, right? So that's fraction of attributable risk. How much of this risk for an extreme event above this threshold was due to climate change? Okay. However, the public still in the end often insists on a yes/no answer. So this stuff still sort of boils down to yes/no, even though there's an underlying discussion about it. Was a once in a 1,000-year event, once in a 50-year event, or the risk has gone up by a factor of 3, or various other terminologies that are more probabilistic. Okay, so let's revisit this risk-based approach now from the framework of weather forecasting. And we're going to use a hypothetical example of daily maximum temperatures. In fact, I'll show you some data motivating this in a moment. But we're also going to take a different approach and develop attribution rubrics whose performance can be assessed from the same information used in traditional risk-based assessment. So the same kinds of statistical curves I just showed you are going to be used to assess these attribution rubrics. Okay, so the question we're going to ask is a particular high temperature, extreme high temperature, we're going to call it Tmax, boosted by global warming. And so here's some data analysis from a paper by Hansen. I just cut out a couple of 4 panels in a larger figure. And the idea is there was this counterfactual or unwarmed or baseline world from 1951 to 1980. That 30-year period is often used in attribution because the climate was pretty stable back then. And we've got a division of the temperature extremes into warm, cold, and middle regions. And then it turns out that this same kind of analysis, and we won't get into the details of the analysis given the lack of time, suggested that in the 10 years between 91 and 2001, if we average over the northern hemisphere, the temperature anomalies had shifted by more than a standard deviation toward warmer climates, and also there'd been some change in the variance too. You can see it's a little broader distribution. Okay, so that's our motivation. We're going to keep things simple, and we're going to be fairly conservative too. So we're just going to imagine that the mean daily high temperatures have only shifted by half a standard deviation. This is a whole standard deviation, or maybe even, we're going to imagine they just shift by half a standard deviation from the control climate mean, which we'll denote by mu, CO for control. And if the variance remains the same, this will make it easy to draw curves, but you can do this for all kinds of distributions. They don't have to be normal distributions. If you got enough data to plot the statistics, you can go to town. Okay, and we're going to define extreme high temperature as a temperature that exceeds the mean in the unwarmed world by 2 sigma in this distribution. So what does that amount to? That occurs 2.2% of the time in the control or counterfactual climate. And so that would be saying there's 2 days per summer in the control climate that are extreme high temperatures. So I'd argue that's reasonable, but we should actually talk to people like Kristie about health impacts and so on. But there's one advantage to this whole approach to pick something that is, not something that happens once every 10 years, because you do not have to so accurately define the tails of your statistical distribution to get somewhere. Here, tails can be very hard to define based on limited data. And here we're just using the stuff that's 2 sigma to the right of the mean. Okay, so now let's propose a rubric to answer this question. The question, once again, is a given extreme high temperature boosted by global warming? And a rubric will be yes, if the temperature exceeds the mean by 2 sigma. So now you think about that for a moment, you might say, So what's the probability of detection if we do that? Let's draw the picture for our situation here, which we have the control climate. Here's a normal distribution. We have the current warm climate that's shifted by half a standard deviation. On the lower axis here, we have standard deviation as the bottom axis plot. So everything's all normalized by standard deviations, right? So here's our shift of half a standard deviation. Out here at 2 standard deviations warmer than the mean, we've drawn our threshold, and we've got 2 areas blocked off here. The amount of time you would have got a temperature in the control climate out here is given by this area, blue in B, and then A, we're going to let be this little pink area up above. Anyway, what's the probability of detection, given that we have defined extreme events to be any event warmer than 2 sigma about the mean? Well, the probability of detection is, and again, I wish we were in person and I could take the time to actually get a response, but I hope you all thought about this for a second, because the probability of detection is, of course, 100%, because we just said whenever we have an extreme, we're blaming it on climate change. I mean, can you believe that? This is, we're saying whenever we have an extreme, we're blaming it on climate change, right? So it's wonderful we have 100% probability of detection, but what's the false alarm ratio associated with this? Well, the false alarm ratio is going to be the number of false warnings over all events, right? So it's going to be, in our little area here, it's going to be B over the total number of events that could occur, A plus B, which is actually the same terminology we had for the weather earlier. And it works out to be 34%. Okay, so in comparison to tornado warnings anyway, this is not really so bad. But you still would probably be a little nervous about saying, oh, well, anytime I've defined an extreme event as 2 hot events per summer anytime I get warmer than that controlled climate threshold, I'm blaming it on climate change. People are going to be breathing down your neck saying, well, wait. 2% of the time this was happening anyway. So let's be more conservative. Okay, so let's say we're going to make our rubric tougher. We're not changing our definition of extremes. We're just saying we're not going to label it as due to climate change unless our temperature exceeds the controlled climate mean by now 2.5 sigma. So what that does is it moves the attribution threshold out, right? We're still calling these extreme events if they're warmer than 2 sigma about the controlled climate mean, but it's moved our attribution threshold over here. So we still have the false alarm ratio is now this little b over this a plus b. If you evaluate it, it turns out to be 27%. So we knocked that down some, and we're no longer saying everything is due to climate change. What happened to the probability of detection? The probability of detection was 100% before. What is it now? Well, the story is that there are these events here in this area labeled C, a brighter pink, that are actually due to global warming. We're not got this stuff down here, just this part, that aren't being attributed to global warming. The probability of detection is going to be A over A plus C, and it has dropped all the way down to 38%. Okay, so notice that in trying to tighten up, just like the case was with tornado forecasting, if we try to reduce the false alarms, it costs us in probability of detection, and it costs us a lot. Right? The story is the change in the false alarm ratio, we reduced it by 7%, reduced the probability of detection by 62% by going to this more conservative rubric. And if we were to keep doing this and go to even more conservative rubrics, saying, look, 27%, quarter of the time, is still not so good. Let's start looking at events where the temperature is 3 sigma warmer than the controlled climate mean. In that case, we dropped the false alarm ratio a little bit more, and the probability of detection has gone totally into the toilet, right? All of a sudden, we're not detecting hardly anything. Okay, so let's just take a quick look at other National Weather Service performance metrics for other hazards. Tornadoes are the hardest to forecast, and arguably maybe you're willing to accept a higher false alarm ratio to avoid getting killed by a tornado. The false alarm ratios for things like severe thunderstorms, flash floods, high winds, and winter storms are listed here. Notice they range between about 45 and 55%, which are all above the false alarm ratio we had for that extreme event attribution. Probabilities of detection are the next line here, and they're up 82 to 69%, right? And we'll skip the lead time. We don't need to look at that. Okay, so let's get to the conclusions here then. I'm getting, I think I promised to stay within 25 minutes. I think I did that, hopefully. So the idea is we need to be aware that if we insist on a very high degree of certainty before attributing an extreme event to climate change, we drive the probability of detection towards 0, and that decreases in the probability of detection greatly exceed decreases in the false alarm ratio as we consider these trade-offs. Current tornado warnings tolerate a false alarm ratio of 70% to preserve a probability of detection of 50%, and the other warnings are in this range I was just mentioning. False alarm ratio is sort of around 50% actually. Probability of detections, 70 to 80%. Okay, so another thing to think about now in terms of relating climate change attribution questions to hazardous weather warnings, that the long-term effects of underwarning are worse in the case of climate change. You know, if we underwarn for a tornado and a severe tornado occurs and you didn't get a warning out, you're in trouble. And if it's a bad enough tornado, there'll be congressional investigation, there'll be finger pointing, there'll be a number of things. But what will not happen is next year's tornadoes will not get worse. Okay. Whereas in the case of climate change, if we fail to properly alert the public and we don't get some response, well, the problem just keeps getting worse, right? Okay, and then I want to point out one other important thing is we've had these two things called FAR, the false alarm ratio and the fraction of attributable risk from traditional risk-based climate attribution. Conventional risk-based attribution focuses on the risk ratio and the fraction of attributable risk. They're both easily expressible in terms of the false alarm rate, the way we defined it in relation to those statistical distributions. For example, the fraction of attributable risk is 1 minus the false alarm ratio. The risk ratio is 1 over the false alarm ratio. So this has a subtle message in it that shouldn't be lost here, which is that previous work based on epidemiology and climate change attribution has been focused entirely on false alarms. And one of the messages of all this, if we think about the weather forecasting end of the business as well, we need to also consider the probability of detection. We can't just always be arguing about whether or not it's a false alarm. We have to ask people, do you want a warning? And if people want a warning, that sea level rise might wreck their little place in Key West, for example, then they need to think about the probability of detection as part of the warning and not just argue about whether or not we have a false alarm. Okay, so that's just a reference for this, and that's all I have.
Isn't the core problem forcing a continuous probability function into simple binary language? Shouldn't we give answers not as yes, no, but as probabilities as forecasters do for rain?
So I assume that's to me, right?
Yes, I think so.
Okay, so of course, this is the way that the scientists want to answer it. They want to not force it into binary language. But I've actually, as I was starting to present this work, several people who have been much more involved in attribution than I have came up to me and said, you know, the story really is that in the end, you can talk to a reporter, you can try to talk about the risk ratio, fraction of attributable risk, it's going to come out as yes or no. And so I think that we don't really control this narrative as much as we might think. It's exactly true. Well, the most information is actually the statistical distributions themselves. For example, you don't necessarily even need to distill them into risk ratios and fraction of attributable risk. You can present the whole statistical distribution, say, now look, and start talking about it. But the public often really wants a yes, no answer. Is it going to rain or not? Is there going to be high wind or not? Was this event due to global warming or not? And so it's hard to avoid this binary response, I'd argue, even though one might say, yeah, we really shouldn't do that. In fact, arguably, I don't want to make this too long an answer, but arguably, even in weather forecasting, people are far more insistent, even for simple things like rain, about a yes, no answer than a probability.
So another comment in the chat, tornado watch and tornado warnings, which are sort of these are two different categories or two different things. Is that a good way to think about it?
Well, that's all true, except none of this had anything to do with tornado watches. Okay, so the story is the National Weather Service, who have not properly engaged conversations with social science experts and so on, have two terminologies, watches and warnings, that sound almost exactly the same. So the first question is, can you even remember the difference between a watch and a warning? And most people can't unless they drill on it. And so the story is the watch is issued earlier and it says, kind of become alert, start to think about following our forecasts and so on, because we at some point might issue a warning. And if we issue a warning, we want you to do something. Okay, so basically none of this involved watches.
So one more question, what about a potential estimate or range of costs?
Is this probably to me, or is this Kristie? This could even be Kristie.
It could be either one of us, and it's the same challenge of what do you do? I think the first detection and attribution was Miles Allen on the heat waves in Europe in 2003. And I forgot the number exactly, but said that climate change increased the probability of the event by the two events by, I don't know, was it 75%, 3/4? And people just don't know how to interpret that, is what it comes down to.
Yeah, so if I can chime in too. So yes, there's this idealized notion that you want to estimate the costs of the climate change and the costs of mitigation and adaptation, and you come up with an answer about what you should do. But in fact, these things are all very, very poorly defined. So it's a bit of a hypothetical idea that you can actually come out with some sort of optimization function that you then react toward. But the other thing that's also very much true is often the people that pay the costs are not the ones that are most affected. So the whole thing just kind of is, to my mind, a little bit of a, so I'm being maybe a little flip, but nevertheless, a little bit of a wonderful thought exercise. But the by the time you get to the point that so often the impacted people aren't paying the cost anyway, the people who have to pay the cost aren't impacted. I mean, the whole thing becomes politically quite difficult.
So
And it's also
there's
the-
one question that would be,
Sorry, I'll just,
go ahead, Chris. I was going to ask you a question, but go ahead.
yeah, there's a compounding issue of how you define the event. So some events have been defined in terms of frequency and some events defined in terms of intensity. And when you take the same event and do frequency and intensity, you can get different results.
Right.
Falls out from what Dale had to say.
So Chris, I'm going to direct this at you,
Okay.
but they said it's to both. Any thoughts about how to think about these issues in complex systems where causality is not fully elaborated or proven, attributing food system impacts from now more probable weather-related shock?
Yeah, thanks, Jeremy. It is a really good question. And there is a group of us who are discussing these kinds of things. We're struggling with those issues, and they're non-trivial, as you've implied in the question, to try and sort out how best to frame the question. And we're spending more time on how you frame the question than how you do the math and the statistics. And the answers really matter. Priorities are being set. Billions of dollars are being spent on adaptation. People want to set their priorities. They want to know how much they should invest in trying to reduce the damages from extreme events versus reducing the damages, for example, to the nutrient density of our food. So the long-winded answer is yes, lots of thoughts on it, and really haven't made a lot of determinative progress at the moment, but hopefully there will be some soon. Dale?
Well, I don't know that I have too much I can add to that. Although you did bring up an important point, which is that there's two different questions can be asked. And how much more severe was this event because of climate change, or how much more likely was it? Those do have different answers.
Yeah.
And I think to some extent it's just a completely undetermined and almost impossible problem to really imagine that you can come up with anything that's as mathematically rigorous as people might want about where the trade-offs are.